Mr. Blackmeyer.
I'm Nathan Blackmeyer. I'm team leader for Group 1. Our project is called Killer Paint. We have an automated paint booth. It's automated in that the entire process is completely controlled by computer, and you just hit a button and the entire project will do its thing. Our group members are Mr. Adams, Mr. Felton, Mr. Loaf, and Mr. Creed, and I'll pass it on to them.
Okay, when our project first starts, our robot's required to go to a home or nest position, and once it gets to this nest position, all the solenoids are engaged on our on-ramp, which prevents them from going on the conveyor. And what we do is we load them up one by one, and we turn the key. The first solenoid drops, letting the car roll onto the conveyor. And when the car gets onto the conveyor, it comes across this first sensor. And when it trips this first sensor, it turns on our paint booth, which is represented by green high-intensity LEDs. And what it also does is it also changes the two solenoids on our on-ramp, which moves our cars farther down on the on-ramp, getting the next one ready to go. And when the first car reaches the second paint booth and it hits that sensor, it turns on our side-to-side painting, which is again represented by high-intensity LEDs. And it also changes the solenoids, which let our second car get on the conveyor. And that successfully lets our cars get on the conveyor one by one without putting two cars in one station at one time. And I believe next is Mr. Felton.
Well, Mr. Felton, and once it comes off the second paint booth, it's going to hit the sensor, and it's going to start dropping the water down, which we got a water pump under the table, which you can't see it. And it's going to pump water on that car, and that's going to represent our clear coat. And once it gets done with that, it's going to lead into this dry booth, and hit this sensor. It's going to turn this big industrial fan on. And once it gets dry, it's going to lead it over to our proximity sensor. Sorry. And we had some problems. We had to build a trough right here so it lead our water back into our reservoir so it keeps the belt and the table pretty dry. And Mr. Lowe will talk about the rest.
Okay, after the car reaches the end of the belt, we have an inductive sensor here, and which will trigger the robot to come down, pick up the car, swing over here, put it on this track, and we have two PM motors mounted under the table which spin these wheels, shoot the car down the track, and that's kind of like an add-on thing we did, I guess grand finale if you will, just so we could get the car out of the way of the robot.
I was in charge of our programming and also our interfacing for this project. The entire process is controlled by computer in that every single input and output has to go through the PC in order to be processed and checked. We use two interface cards in the PC to actually control everything, which those interface cards then go to our control circuits. Underneath the table, which you can't see, is a control circuit that services the robot. It controls the direction of the robot and also watches all of the bump switches all over the robot that serves our inputs, and also lets the computer know where the robot is in its different axes. Our circuits over here that you can see on the table, the first circuit right here takes care of the outputs for all of our devices on the table, like the different motors and LEDs. It's driven by MOSFETs. The last circuit over here serves as our input stage. It checks the inputs from the table and as far as our different sensors on the line, and then inputs that to the PC. Our PC is programmed in assembly language, which is a type of machine code. It's programmed to where all the sensors are checked at all times, to where for maximum efficiency it can go on, everything can move at once. So that even while the robot's moving, the ramp will go on and move and have the next car waiting for it whenever it gets back. That way everything can go through the line as quickly as possible. The entire program is menu driven so that it's user friendly. We have two stop switches on the table that will stop the project if anything happens and you need to stop it. Also we have our start switch that keeps the process from going until we turn the switch and we're ready. I'll turn it over to Mr.
All in all, our project went pretty good. We started like the second week of this semester. I'm kind of give you an overbase of the whole thing. Our cars drop in, they come down, the paint booths, both paint booths paint the top, bottom, and sides of the car. The clear coat comes on, the industrial dryer dries it, robot picks it up, shoots it down the car. We ran into a few problems with our project. We had a problem with our first paint booth over a couple months, over about the 2 months, the last 2 months. Our LEDs started to dim down, and so we had to replace those. Also, we started with 2 computer fans as our drying booth and realized that putting water all over our circuits and all over the table, that we needed to get it off our belt so it didn't drag it from one side of the station to the other. Also, we found out that our robot wouldn't pick them up all the time, so we had to put a little piece of plexiglass in the way there to shift the car over if it wasn't far enough over. Other than that, Mr. Loaf here painted all of our top of our table and put the skirt around. We got our project done about 2.5 weeks earlier than most of the projects get done. We were kind of proud about that. So other than that, we'll show you how it works.
To start our process on our program, we first have to give our interface cards a stop command, which initializes them and outputs everything to the correct either a high or low bit in order to actually stop the entire project. Which once that's done, then we can kick on our power supplies. And at this point it does get a little noisy because of our car motor. And the first thing that the program will do is nest the robot left and right, and then at that time we can turn the key and it'll start the project. There we have our complete project. Now at any time you could press the stop switch, and as you see it kicked out the loop and stopped everything on the table. Just keep it from moving. And that's our project. Do you have any questions or comments? We had over 200 man hours in this project. A lot of the time was spent during class, but we also did have overtime where a couple of us would come in after class and work on it for a while. Mr. Creed put in a lot of time during the beginning of the project, getting the table built and whatnot, and then after that it switched off to me for trying to get all the programming done, which was very time consuming.
Okay, this question goes to everybody. If you had it to do over again, if you were just starting today, what would you do different?
I'd put a little bit more planning into it, because we pretty much decided we were just going to jump in and start building, get everything built first, whenever we probably should have maybe went through and thought about more what we're going to build and how we're going to build it and stuff. But maybe it's a little bit more planning ahead.
Okay.
I think it'd be neat to have another robot on the other side, so after it gets shot down the track, that way the robot will recycle the car, put it back on the loading track. That'd be kind of neat.
If I could probably do it over again, start it over again, I'd probably end up doing something different. Since I did all the mechanical, I'd probably end up doing something different totally on the whole board. I wouldn't use quite as much metal as we did. I don't know what I'd use, but I'd use something different. We had a lot of problems with the belt getting hung up on the railings, and the belt not being strong enough to hold the car without the railings, so we had to have the railings there. Other than that, there's just little bitty things that you could do different that would make your project better, whether or not you do it right the first time or not. So.
And plus, it's something better to catch the water with. Maybe on the other end right there. We keep on having water drip down. Maybe build something better to catch that water that was all coming off the belt line there.
I guess the only thing I'd change would probably be in my programming. I would like to have gotten more in the menus and also in the interactive side, but everything works and functions, so it's really not necessary.
Do you feel that the project as a whole is a success?
I believe so. We got it done early. Everything worked the way it's supposed to. And actually the process went along pretty fast. I mean, it could churn cars through the whole deal pretty quick.
Okay. Gentlemen, good job. You did a good job.
Hello, my name is Tyler Rhodes. I am team leader of Group 2. Our automated process is we made a minting machine. Basically, it just takes a coin from another part of the station, cuts it to size, stamps it, buffs it, gets it ready for shipping. Our team members are Mr. Sweppy, Mr. Duncan, Mr. Bousson, and Mr. Kinder. I'll turn it over to them in a second and let them explain the whole process in detail. My main job was I was in charge of the programming aspect of the whole thing. I did all the programming for the robot and actually had to interface the robot and everything to the computer. The robot is simple. We attached an electromagnet to the arm of the robot, which picks up the coin from the small belt. The small belt represents coming from another process, such as cutting the coin down to the diameter that it needs to be for the final stages. Once it picks it up, it moves it over to the main conveyor. Once it's on the main conveyor, it de-energizes the magnet and returns the arm back to the home position. Once it does that, the main conveyor starts up and moves the coin down the line to the next process.
After the coin moves down the conveyor to this sensor right here, the sensor picks up the coin and starts a program that's 42 lines long, and it'll simulate a laser cutting the coin to the proper thickness, and these LEDs will run forwards and backwards one time to simulate the laser, and after it reaches back to the first LED, it starts the belt over and moves on to the next station.
Once the coins are cut to size, they move on down the line on the conveyor belt, and these plexiglass slides are used to guide them on the right path of the belt, which will be needed for the next step in the process.
Once our coins are separated, they go down to two inductive proximity sensors. Once they are picked up by the sensors, we have two solenoids that are connected to levers that power our levers to do our stamping. Once they are stamped, they are sent down to the next process.
The next process involves a buffing wheel, and once the coin reaches the proximity sensors, it will send a voltage out to comparator circuits, which will energize the motor that runs the buffer wheel for a set interval time.
Once the coins are buffed, they're sent down the line on the conveyor belt, which will then dump them into loading bins for shipping. In these boxes are two proximity sensors, which allow us to know whenever they become full. Once they are full, this light will emit.
The final thing to explain would be the emergency stop switches. If anything goes haywire or a safety issue comes up, you just hit the stop switch and it kills all power to everything at once. It also allows you to fix any problems that might went wrong on it at the time. Demonstrate on the last coin that this process of using an emergency stop switch, and you can turn it back on and it'll run where it left off.
We'll now demonstrate the whole process. here we have noticed that this coin was not cut to the proper size. So in turn we will stop the process, take this coin out of the loop, and then start the process back up. That is our presentation.
Okay, this question goes to everybody. If you had it to do over again, if you were just starting today, what would you do different?
I would attach our gears to our main shafts differently. We ran into problems. We pretty much tried to sink them down with nuts, and once everything got running and stuff started wearing out just a little bit, the nuts backed off, which in turn these would spin on our shaft and our whole conveyor wouldn't turn. This caused several problems because you have to take everything back apart just to take this shaft out and reattach this. So to start off, I would have used some sort of an epoxy, which is what we did to attach our main gears to our shafts.
If there was one thing I would change, it would be the type of belt that we used for the conveyor system. This belt that we used, it wasn't one solid piece. We had to join it together, and when we first joined it together, we used wire, and the wire was actually tripping our sensors and giving our false triggering, and we had everything going haywire. It was a big mess. And also it would mess up the coin height on our slides, and it wouldn't, if the coins ever landed on our seam, it would throw everything off. So we ended up trying a couple different methods of fixing that. We first tried to melt it together, and that didn't work because of the strength issue. And then we ended up finally fixing it by using fishing string, and that's what we have now. But every now and then it gives us a little trouble. If I had one thing to change, it would definitely be the type of belt we used.
I would have changed something. I would have did a little more planning. We had to totally redesign the loading station. The first one just didn't work for us at all, and it took a lot of time to rebuild it. And also I would have tried to find a way to program it to where the system runs constant instead of just one coin at a time. It would bring another coin after the first station, to where right now it's got to go all the way to the end before it'll bring the next coin back onto the conveyor.
I'd probably brush up more on my types of sensors. Probably would also brush up on my analog to digital conversion. Try to figure out more ways for that. In the end, I probably didn't see how simple, really, sensors were, but I did actually learn a lot more about sensors than I knew in the past. So.
If I were to change something, it'd be putting more planning in the project, because like I said, we had a lot of problems that we had to deal with. I would definitely deal with both conveyors, because both conveyors gave us a fit. I mean, we got the bugs worked out with trial and error, and I mean, more or less, I mean, conveyors gave us a lot of problems.
Gentlemen, good job. You did a good job.